रहमत फरीद
जी हेलो, अस्सलाम वालेकुम।
वालेकुम
जी वालेकुम अस्सलाम सर।
सर, कैसे हैं?
जी बिल्कुल ठीक, आप लोग कैसे हैं?
अल्हम्दुलिल्लाह।
अल्हम्दुलिल्लाह सर। अस्सलाम वालेकुम।
वालेकुम सलाम।
अस्सलाम वालेकुम सर।
जी जी वालेकुम अस्सलाम। Okay, let me call your attendance. Abdul Razak. Abdul Razak. Eman Gul.
Present, sir.
प्रेजेंट सर।
Amir Abbas. Amir Abbas.
Present, sir.
Asad Mahmood. Asad Mahmood. आसमा बीबी। जी आसमा बीबी। अवैस अहमद।
प्रेजेंट सर।
आयशा लियाकत। दिलावेज।
Present, sir.
इजाजुल हक।
Present, sir.
फरवा जफर।
प्रेजेंट सर।
गुलाम मुर्तजा।
Present, sir.
मरियम मंजूर।
Present, sir.
मोहम्मद अहमद फरीद।
Present, sir.
मोहम्मद फियाज।
Present, sir.
मोहम्मद फियाज मोहम्मद अनवर।
प्रेजेंट सर।
मोहम्मद जहीर। मोहम्मद अकीरुल अजीम। नगीन फातिमा।
यस सर।
निमरा खलील।
Present, sir.
नूर रहमान।
Present, sir.
नूरुल एन फारूक।
Present, sir.
नौरीन कौसर।
यस सर।
नौशीन निसार।
प्रेजेंट सर।
रमीजुल हसन नैयर।
प्रेजेंट सर।
समीउल्लाह।
Present, sir.
सुमैया लाल।
प्रेजेंट।
सैयदा अरीफ।
प्रेजेंट सर।
उमामा शहजादी।
प्रेजेंट सर।
उमर फारूक। उसामा हबीब। जुलेखा आफ्ताब।
प्रेजेंट सर।
के
Assalamu alaikum, sir.
जी वालेकुम सलाम.
सर मेरी अटेंडेंस लगा दे असद महमूद.
Okay. Let me recall the names who are absent. Asad Mahmood, Asma
Yes, sir.
Bibi, Asma Bibi, Aisha Liaquat, Mohammad Zahir, Mohammad Amirul Azim, Umar Farooq, Usama Habib. Okay. Hmm. जी अनम रियाज,
Present, sir.
सादिया फारूक,
Yes, sir.
okay. All right, let me share screen. So okay, last time we discussed some examples of metric spaces.
सर आवाज बहुत कम आ रही है.
Okay, so let me know if you can hear me properly. जी आवाज आ रही है आपको अब?
जी सर. Yes, sir.
Yes, sir.
So the last example we discussed was of LP spaces, the sequence spaces. So we proved that LP for P greater or equal to 1 less than infinite is metric space. To show that LP is metric space with metric D defined as So for all x is a sequence xi and y is a sequence eta I in LP. So remember x belong to LP if xi I mod I from 1 to infinite RP is less than infinite. So in order to show that it is metric space LP with the metric defined as this formula, we proved Minkowski inequality. To prove Minkowski inequality, we proved Holder's inequality and Cauchy-Schwarz inequality. Okay. So now we will discuss some topological notions. Topology of metric spaces. So in topology, so let Xt be a metric space. So for x not belong to x and a real number R define the following sets. So the first set is B X R. So it consists of B X naught R. B X naught R is a set of those X belong to X such that the distance of X with X naught is less than R. So this set is called open ball. Open ball with center at X naught and radius R. The second set we define is closed set with center at X naught, radius R, and this set is consists of those X whose distance from X naught is less or equal to R. Number third set is S X naught R, that consists of those X whose distance from X naught is equal to R. So that is called a sphere. This one is called B tilde or B bar. You can use bar as well. So B bar is, maybe bar we will use for something else. That is fine. So it is closed ball with center at X naught, radius R. So S X naught R consists of those X whose distance from X naught equal to R. So open ball is a set of all those points whose distance from X naught is less than R. B tilde closed ball is whose those set of those points X whose distance from X naught is less or equal to R. And Sx naught R is those points whose distance from X naught is equal to R. So you can see that this set is actually equal to Bx naught R minus this minus is the set difference. So this set is called a sphere with center at X naught radius R. Okay, so when we discuss the topology of metric space, so these are the three basic sets we need. So what is a topology? You must have heard this name before. So let me know if there is anyone who never had heard of this word topology. So we will define what topology is, right? So for now, we have these three sets. What we call these sets open ball, closed ball, and sphere, respectively. So these sets have a point x naught, we call it the center of these sets, and R, a real number, which is the radius of these sets. And the definition depends on the metric D. So xt is a metric space, x naught is a point in X, and R is a real number. Consider this example, few examples first. So what if X is equal to R and maybe X naught is equal to 1 and R is equal to 2. So what will be this set B1, 2? So let me define the distance on R as well. So distance is the usual metric x minus y mod, right? So for all x, y belong to R. And x naught is equal to 1 and R is equal to 2. So B1, 2 is the set of those points in X whose distance from 1 is less than 2. So that is the set of those real numbers. Distance is defined by 1 minus x mod less than 2. Or maybe you can write it as x minus 1 mod less than 2. So as x minus 1 mod less than 2, if and only if using the properties of real number absolute value function, x minus 1 mod less than 2 greater than minus 2. So if and only if x is less than 3 and greater than minus 1. So if and only if x belong to minus 1 and 3 open interval. It is an open interval from -1 to 3. So this set is equal to -1 to 3 open interval. So can anyone tell me what will be the B tilde 1, 2?
Sir, close interval.
So close
minus
interval
3.
-1 and 3.
Yes, closed interval -1 and 3. And what will be the S 1, 2?
X is equal to 3.
-1, 3. -1, 3.
-1, 3. So it is the set of those points whose distance from 1 is exactly equal to 2. So distance of -1 from 1, distance between -1 and 1 is equal to 2. Distance between 1 and 3 is equal to 2. So you can draw this real line somewhere. So we have 0, 1, and that is -1, 2, and 3. So this distance is equal to 2 and this distance is equal to 2. So there are 2 points in the sphere. So if you consider x is equal to r square and metric d defined as dxy is equal to x1 minus x2 square plus y1 minus y2 square. So that was d2 metric, right?
Yes, sir.
For
Yes,
all
sir.
x equal to x1, y1, and y is equal to x2, y2 in r square. So b, for example, let x not be this point 0, 0, or maybe 1, 1, and r is equal to 1. So then bx naught r is the set of those ordered pairs whose distance from x naught is less than 1. So as dx naught x less than 1, so that is equal to let x is equal to a point, arbitrary point a b in r square. So that will be equal to a minus 1 square plus b minus 1 square root less than 1. That is a minus 1 square plus b minus 1 square less than 1.
1.
So what is it?
Sir, it is a open circle
Hmm.
with center at 1, 1 and radius less than 1.
Center at 1, 1
1, 1. Yes.
and radius
1.
Radius
radius
less
1.
than 1.
So So it is actually the interior of the circle, right?
Yes.
With center at 1, 1, radius 1. So boundary is not included. Because at boundary, those points lie on the boundary of this circle whose distance from 1, 1 is equal to 1. But we are not considering, we are considering the open ball where distance of points is strictly less than 1. So it is the interior of circle. So you can say that B x01 is the interior of circle with center at x0, radius 1. So what will be the B tilde x0 1?
So closed circle in which boundary is also included.
So boundary is also included. So that is 1, 1, 1 radius circle. So that is, so this will be the whole circle, interior and the boundary. And what will be the Sx01?
Only boundary.
Yes.
Only boundary.
Only boundaries.
Yes. So Sx0 will be this one, the blue one, right? Okay. So we considered some other metrics as well on R square. So x equal to R square d infinite xy. We define maximum metric x1 minus x2 mod and y1 minus y2 mod. And then we have another, yes.
सर एग्जांपल
Sorry.
2 जो है ना इसको रिवाइज कर दे थोड़ा सा.
Mhm. And there was another metric d1 xy that is equal to x1 minus x2 plus y1 minus y2. So where x is equal to x1, sorry, x1, y1, and y is equal to x2, y2. So the question I'm leaving for you is, so check the bx0 1. So and b tilde x0 1 and sx0 1. So find these sets in R square with these two metrics.
And sir, x node journal lena.
For x0 is equal to 1, 1. For x0 is equal to
1 1.
1, 1.
ठीक है.
So we are in R square, so you can plot these sets. So जब आप इसको find out करेंगे तो you can plot these in R square, right? So you will see that maybe you will get the sets like this one. So this type of sets are open sets, and maybe you will get check like this one, right?
Yes.
So geometry, the shape depends on the distance. So if you can plot something, so maybe you will get the different shapes of open ball, and that depends on the distance function. So you change the distance function, you get the different shape. So
Yes.
what happens, for example, in the case example number 3. So if xt is a discrete metric space, if x for x equal to r square, sorry, r, and d is discrete metric. So discrete metric defined as dxy is equal to 1 if x is not equal to y, and 0 if x equal to y. So in that case, for example, what will be this open ball?
Zero.
0 less than 1.
Open ball consists of those real numbers whose distance from 1 is strictly less than 1, and distance of 1 and x is less than 1
All real number set.
if and only if. So you have d is a discrete metric now on R.
Yes,
So
sir.
in discrete metric, there are only two possibilities, that distance between two elements is either equal to 0 or equal to 1. So distance between any two number is
जी सर
there is only one possibility, that the element it is 0.
It is
So
0.
distance can be less than 1 and it will be 0. If distance is 0, d is metric, so both elements are same. So that is
Straight line
possible
passing.
if and only if d1x is equal to 0, and if and only if x is equal to 1.
X equal to 1.
So
Straight line.
It might not be the straight line in the case of R, it is just a single point.
Point.
Yeah.
Okay. Yes, sir. Sorry.
So maybe you can check, well, it will be point in. So for any radius, so what about closed ball? 1, 1.
So the set of real numbers.
Yes.
It's also x equal to 1.
X equal to 1 and x equal to 0.
No,
But
it's
it will
x equal to
satisfy
1.
all real numbers. It will satisfy for all real numbers.
Yes. So the distance is less or equal to 1, right? So for
Yes.
all elements of the space, so there are only two distances, no?
Yes.
But this discrete metric by definition is less or equal to 1, right?
Yes.
So it is the set of all real numbers. Okay. So what about the open ball? 1 with radius 2.
One with radius 2.
So
Again,
the set of real numbers except 0. Sorry, 2.
x equal to 1.
So that is the set of all real numbers whose distance from 1 is less or equal to less than 2. And discrete metric by definition is for all xy, it is less than 2 because discrete metric gives distance either 0 or 1. So that won't it be the whole real number? The set of all real numbers. So that means the open ball, closed ball, and sphere depends on the metric you have on the set. So now we can define the topology. Topology what is topology? Anyone?
The set of all open sets.
Set of all
Open sets.
Set. That we have a non-empty set X. A collection of subsets of X is called a topology. If X and non-empty set, if X and set empty set lies in that collection, also union of any number of that collection lies in that set, and intersection of finite number of sets means subsets lies in that set.
So let X be a set, maybe non-empty set, a collection of subsets of X. So you can call this collection, you can name it if it is tau, or a collection tau of subsets of X is topology, is R topology on X if it satisfies three conditions. Somebody was telling me the condition that empty set is there, the set X itself is there, and arbitrary union of open sets, arbitrary union belong to tau for all A alpha belong to tau. So if you consider any number of sets in tau and consider the union is in tau as well, and finite intersection is also there. I1 to n belong to tau, where I from 1 to up to n in tau, right? So these are the three conditions. So somebody was telling me that the collection of open sets. So
Yes.
actually in topology, what are the open sets? So open sets are the members of topology, right? So whatever is the member of topology, that is an open set. You can call it an open set. There is another definition of open set in the sense of neighborhood. So a set is open if every point has a neighborhood in which point belongs and neighborhood is contained in the set. So that is an open set. So actually, let me define in the case of metric an open set. So let Xt be a metric space, a subset. M is called, M is an open set. If it contains a ball, an open ball, about each of its point.
points.
So for example, if we have this metric space X and this set is so this is this is a subset, right? So if you pick any point in this set and if you can draw an open ball around that, so you can draw an open ball of radius any positive number. For example, if you have this point, so you can draw an open ball of radius so that it is contained in the set, it remains in the set. So if you can do this for each and every point of M, then M is an open set. So if you cannot do this for some point, if there is a point in M, so that whatever open ball you draw around that point, it is not contained in M, then M is not an open set. So M is open if you can draw an open ball around each of its point, which is contained in the set. So if set contains an open ball around each of its points, then it is open. And a subset M of X is closed in XT if its complement, M complement, which is equal to X minus M, is open in XT. So first we defined open set. And what is an open set? If there is a ball around each of its point and ball is contained in the set. And closed set in a metric space is a set whose complement is open. So complement, what is a complement of a set?
X minus M. Universal set
X.
minus set.
Yes. So complement of M in X is X minus M. So those elements which belong to X but not M. So in M complement will consist of those points in the space which are not in M. So that is complement. So if complement is open, then the set is closed.
Open.
So you can see that Bx naught epsilon is an open set. In XT. Show that. So you can do this exercise, right?
Yes.
So how will you show that? You will assume an element in this Bx naught epsilon, and you will
Draw a neighborhood.
yes, you will show that there exists an open ball which is contained in this ball. But you will assume any point, any arbitrary point in Bx naught epsilon, and you will show that there is an open ball around that point which you will select in this set. And that open ball is contained in this ball Bx naught epsilon. And that means Bx naught epsilon is an open set. So do it as an exercise.
Yes.
It is an exercise as well in this section. And in this book neighborhood, there is another definition. I don't know whether we will use somewhere or not, but you can consider neighborhood of a point. is a set n such that there is delta greater than 0 satisfying x belong to b x naught b x naught delta is contained in n. Of course, x naught is the center of this ball it belongs to. So this n is neighborhood of x naught. So if it contains a ball around a point, then it is neighborhood. So it n can be open set or closed set. It is any set, right? So in some books they consider a neighborhood should be open by default, but in this book neighborhood is any set which contains an open set around that point. So then there is a theorem, set of all subsets, sorry, all open subsets of a metric space. Metric space XD is a topology. So you need to show that the collection of all open sets in metric space satisfies those three conditions which we were discussing. 1, 2, 3, phi and x belong to tau. Union of all open set is open. So what is the collection tau? Tau is the collection of all open subsets in metric space. So you will show that phi is open, x is open. Union of any number of open set is open. And then you will show that finite intersection of open sets in metric space is open. This way you will be showing that the collection of all open subsets in a metric space form a topology. And this topology is called metric topology.
सर
Yes.
सर इसके लिए तो एक हमारे पास सेंटर पॉइंट होना चाहिए और एक खास रेडियस भी होना चाहिए किसी भी मेट्रिक स्पेस का जो हमने ओपन सबसेट लेना है
So you need to consider all the open subsets of metric space.
सर आर्बिट्रेरी रेडियस और आर्बिट्रेरी पॉइंट पे करेंगे इसको.
Arbitrary radius or arbitrary points.
रियल लाइन पे भी शो कर सकते हैं सर.
Anyone else? Real line? What are you saying? Real line? Say again. Hello?
पे शो कर सकते हैं.
Real line पे कैसे? Okay, so there is a proof in.
Sir,
Yes.
excuse me, sir.
Gigi.
Sir, we are discussing about the open set. Then open ball और जो हम लोग neighborhood की बात कर रहे हैं, ये दोनों same things हैं. सर कॉज हम लोग एक्स ले रहे हैं वो एक क्लोज सेट है, ठीक है। एम हम लोगों ने लिया है कि ये एक सबसेट है एम ऑफ एन ओपन सेट, और ओपन सेट तब होगा जब इसके अंदर एक हर पॉइंट पे ओपन बॉल एग्जिस्ट कर रहा है, कंटेनिंग करेगा, तो हम लोग कहेंगे ये ओपन सेट है, ऐसे सर।
सो ओपन सेट बिल्कुल ऐसे ही है. So if there is an open ball around each point of a set which is contained in the set,
ऑलराइट।
that set is open. So neighborhood something different. So neighborhood is any set which contains an open ball around that point. We are saying n is a neighborhood of x naught, so there should exist an open ball around x naught which is contained in n. So n can be anything. It can be open set, it can be closed set. But if it contains an open ball around the point, then it is the neighborhood of the point.
राइट सर।
So by definition, by default, every point of an open set. So open set is a neighborhood of every point in it. So if you consider an open set, it is by definition it is neighborhood of each of its point. क्यों? क्योंकि open set है तो there exists open ball around each of its point which is contained in this set. So it satisfies the definition of neighborhood as well. So in this question, this theorem, इसके statement को आप इस तरह से भी लिख सकते हैं और show that xt is topological space. So that means if you have a metric space, you have a topology, collection of sets which satisfy all the conditions of being a topological space. If you have a metric space, you can collect all the open sets in the metric space. So that collection of open sets in the metric space satisfy the conditions 1, 2, 3 on the previous slide. Let me show them. So this one, phi x belong to tau, arbitrary union belong to tau, and intersection belong to tau. So let me, you can write its statement as well, or set of all open sets in xt satisfies these three conditions. Phi is an empty set, belong to set of all open sets, maybe you can call it tau, set of all open sets belong to tau. You need to show that union of A alpha belong to tau for all A alpha belong to tau. Tau is the set of all open sets in metric space. And intersection I from 1 to n, AI belong to tau for all AI belong to tau, where I is 1 to up to n. So, well, I can give you the idea of the proof. So you can have these proofs in different books, text, maybe in this book as well. So phi is open as phi and x are open in xt. So phi x belong to tau. So can you tell me why phi is an open set? in metric space?
सर x तो हमारी मेन मेट्रिक है, उस पे हम जो भी मेट्रिक ओपन बॉल ड्रॉ करेंगे वो सेट के अंदर से ही आएगा, सेट के अंदर ही कंटेन करेगा, तो x इसलिए ओपन है।
ठीक है।
और फाई क्योंकि एम्प्टी सेट है, उस पे हम ओपन बॉल ड्रॉ ही नहीं कर सकते।
So X is open because, so if you draw open ball around any of its point X, that will be contained in X because it is, by definition, it is open ball is a subset of X. It is contained in X. So any open ball around any point of capital X is contained in X. So X is open. So phi is open because we cannot draw an open ball. So phi is an empty set. So there is no point in this set. So when do we say that a set is not open?
When its complement is when it is closed.
No.
So you repeat kar dein please.
So when do we say that a set is not open?
सर जब हम एक ऐसी ओपन बॉल ड्रॉ करें जिसका कोई एक भी ऐसा पॉइंट आ जाए जो सेट से बाहर चला जाए, तो वो सेट ओपन नहीं होगा।
Anyone else? When do we say that a set is not open? In metric space.
I think its boundaries must be closed.
Say again.
I think its boundaries must be closed.
It must be closed.
Yeah, I think.
So, but X is closed as well, and X is
Yes,
open as
sir.
well. So
Both open and
there are
closed.
sets. Yeah, there are sets which are both open and closed. If X is not open,
Open
that
set.
doesn't mean X is closed. So phi is open.
Phi is both open and closed. It's
Yes.
open set.
Phi is
So phi
both
is
open and
open because we cannot contain any subset around which we draw an open ball and it is not contained in the set. हम ऐसा कोई
Yes.
ओपन बॉल नहीं ढूंढ सकते।
Yes, that is more appropriate. So we cannot, there is no such point if we draw any open ball around that point and it is not contained. Why we cannot have such point? Because there is no point in empty set. It is empty. So the definition of being open is by default holds. There is no problem. So we cannot find a point in M5 because it is empty set. Okay. So the first condition holds true, and second condition, for example, if you consider U as the union of open sets where A alpha belongs to tau. So we want to show that this U is open. So what will we do to show that U is
सर
open?
U का एक पॉइंट लेंगे, उसके इर्द गिर्द नेबरहुड ड्रॉ करेंगे।
Yes.
और वो नेबरहुड कंटेन करना चाहिए U में।
Assume X not belong to U, right? So you can pick any point in U. X not be any point in U, arbitrary point, right? So this implies that X not belong to the union A alpha. So by definition of union, X not belong to A alpha for some alpha Alpha is a index, and maybe this kappa is the index set. So here you can define alpha belong to kappa, which is index set. So as A alpha is open, so there is epsilon greater than 0 such that B x naught epsilon, epsilon is the radius of ball, is contained in A alpha, and which is contained in U, which is the union of A alpha. So this implies that U is open because there exists an open ball which is contained in U. Union is the bigger set, so X naught belong to union, so X naught belong to some open set. So there is an open ball because A alpha is open, so there exists open ball. So the third one is also very easy. For example, let AI be open for I is equal to 1, 2, 3 up to n, and B and D is a set which is the intersection I from 1 to n AI. So we want to show that D is open. So here we have shown that U is open and U belong to tau because tau is the collection of all open sets in metric space. So similarly, we consider the intersection and let X not belong to D, arbitrary points. So this implies that X not belong to intersection of AI, I from 1 to n. So this implies that X not belong to AI for all I 1 to up to n. Now we want each AI is open. So there exists, and X not belong to each AI. So there exist R1, R2 up to Rn such that X not belong to open ball Ri is contained in AI and I from 1 to up to n. Because each AI is open, so each AI will contain an open ball around X naught which is contained in AI. So if you consider R to be the minimum of Ri, where I is equal to 1 to up to n, so that means R is lesser equal to Ri for all I. So for example, if you have A1 and then you have A2, and then you have A3, A4 up to so on. So X naught is in the intersection here. So this point is in all the sets, and there is a ball in each set which contain this point and is contained in the respective set. So if you consider the minimum of all the radius, so you will have the ball of radius R which is contained in each and every set. So construct this B X naught R. So that consists of those points whose distance from x naught is less than r. As d x naught x is less than r and r is less or equal to ri for all I equal to 1, 2 up to n. So this implies that if you take, this implies that b x naught r is contained in b x naught ri for all I 1, 2 up to n, and this is contained in ai. So this implies that b x naught r is contained in intersection. So if it is contained in each ai, then it is contained in the intersection. Okay, so this implies that this set D is open. So this implies that D belongs to top. So that means every metric space is a topological space. Okay, so let me discuss something about continuous mapping from one metric space to another metric space. So let me
एक्सक्यूज मी सर
yes.
सर मैंने ये पूछना था कि हमारे पास डिफरेंट स्पेसेस होती हैं जैसे जनरलाइज मेट्रिक स्पेस है या एम मेट्रिक स्पेस है, तो इनकी टोपोलॉजीज हमारे पास डिफरेंट होती हैं, इनकी ओपन वॉल्स भी हमारे पास डिफरेंट तरीके से डिफाइंड होती हैं, तो ये किस तरह से हमें पता चलता है इसकी ओपन वॉल ये बनेगी या किस तरह से हम फॉर्म करते हैं?
M metric, what is M metric?
सर उसकी जो है वो थर्ड जो इनक्वालिटी है ना, वो थोड़ी जनरलाइजेशन है इसकी हमारे, सॉरी उसमें जो है हमारे पास जो फर्स्ट उसकी कंडीशन है ना, उसमें ये है कि डिस्टेंस ऑफ एक्स वाई इक्वल, बट इफ एंड ओनली इफ नहीं आता इनके दरमियान में, और बाकी दोनों कंडीशन मेट्रिक स्पेस वाली हैं। लेकिन इसी तरह के हमारे डिफरेंट स्पेसेस है ना, वहाँ पर हम लोग जो है वो बॉल्स जो हमारे पास डिफरेंट टाइप्स की बनी होती हैं, तो हम किसी भी स्पेस की बॉल बनाते हैं कैसे अगर हमें नहीं पता कि इसकी ओपन बॉल ये, जब आपने अभी मेट्रिक स्पेस करवाया हमें, इसमें आपने बताया ये ओपन बॉल है, तो इसकी फॉर्मेशन कैसे होती है, मैं ये पूछना चाह रही थी किसी भी स्पेस की ओपन बॉल की।
ठीक है, इन जनरल मतलब ओपन बॉल around this x naught is a point of x, r is any real number, and d is a distance function, right? Not necessarily metric.
Yes, sir.
D is a distance function. So the definition is same. So we define this way: whatever is D is metric or D is not metric, something else, distance function with less number of conditions as compared to the metric function. So we define the set of all points whose distance is less or equal to r. So that is the definition of open ball. Maybe you can call it
yes,
a ball.
Sir,
So the definition remains the same. So whatever is D is metric or D is M metric or D is quasi-metric or D is B metric, whatever it is.
So it depends on the distance?
Yes.
Of a metric or that metric?
Yes. So in the first lecture, we discussed some other spaces, like I discussed pseudo-metric and quasi-metric, pseudo-quasi-metric. So for example, one quasi-metric I can write. So x equal to r. So for example, y minus x, if y is greater or equal to x, and if x is greater than y, then distance is
0.
0. Right? So now you
Height
can,
metric.
yes, height matrix. So if x naught belong to x, and you can define a ball bx naught x, sorry, bx naught epsilon, set of those x whose distance is x naught less than epsilon. So dx x naught is less than epsilon. So that means x minus x naught, sorry, x naught minus x is less than epsilon. So you can write it as x is greater than x naught minus epsilon. So it depends on, so usually in usual metric where you have y minus x absolute value, it is just examples. I'm not going into the details, right? So this distance function, so it is the set of all points x greater than x naught minus epsilon. So if you have usual metric, so what is the open ball on R? It is an open interval. But here we do not have that kind of open interval. We have a ray, right? So that start from x naught minus epsilon. X naught minus epsilon is not included. So for example, if x naught minus epsilon is this point, then it is an interval x naught minus epsilon to plus infinite, this interval. So it depends on the distance function, and topology, the definition of the ball remains the same. But then you have to check what kind of sets will be open. That will depend on the definition of ball. So if you have different metric, you will get different balls. So that is a good question, and you can explore. You can start from the different metrics on R square. So and check what are the open balls in this case, and then you can check for the quasi-metric, M-metric, and B-metric, or any other generalized metric. So it is very important to know the topology, because in quasi-metric, for example, quasi-metric, by quasi-metric I mean there is no symmetry property. So this is a quasi-metric actually. So there is no symmetry property in such metrics. Topology is more general. The topology of the metric space is Hausdorff topology. So, but topology of the quasi-metric is not necessarily the Hausdorff topology. Hausdorff topology is T2 topology. So topology of quasi-metric is T1 or T0. T1 or T0 are bigger topologies. T2 is contained in T1. So T2, which is Hausdorff, is contained in T1, is contained in T0, right? So quasi-metrics induce topology which is bigger than the topology of metric. Topology of metric may, what advantage you have in topology of metric, Hausdorff topology, you have many things like the sequences, the limit of a sequence is unique, but it is
Unique, yes, sir.
it is no more the case in T0. T2 से ऊपर आप if you go up in topology, then T2, so you might not have such conditions. So that is why in fixed point theorem in metric spaces you have many tools. So if a sequence is convergent, its limit is unique, and like single point sets are closed in Hausdorff, but they are no more closed in T naught in quasi metric. वहाँ पे ये close नहीं होंगे. So metric, if you are working in different metric spaces like M metric or so any paper in which a new notion of a new distance has been introduced, you will see that the very first thing they do is to define an open set, open ball, open sets. So then they define the notion of convergence, Cauchiness, completeness, and continuity between such spaces. So those notions depends on the topology, depends on the open ball, open set. So let me discuss one such notion. So for example, let me start from R to a function from R to R. Here R with the usual metric. Well, I think I can define in the metric space directly, then we can come back to this case. So let X D and Y D tilde be metric spaces.
सर स्क्रीन शेयर नहीं हो रही.
Oh,
सर पिछली स्क्रीन शेयर कर दे एक दफा.
मेरे पास तो हो रही है स्क्रीन शेयर. व्हाट हैपेंड?
जी सर स्क्रीन शेयर हो रही थी.
सर हो रही है.
हो
अब
रही है
नहीं हो
सर
रही,
शेयर.
लेकिन पहले हो रही थी, लेकिन सर अब नहीं हो रही.
Okay. Okay, let X D Y D tilde be metric spaces, and F is a function from X D to Y D.
सर पिछली स्लाइड एक तक
T is a function. So T is a function from X T, from one metric space to another metric space. So T is continuous at X naught, which is a point in X, if for every given epsilon greater than 0, there is a positive number delta greater than 0, such that d x naught less than delta implies d tilde dx naught less than epsilon. So remember, if d tilde equal to if dxy equal to d tilde xy equal to x minus y absolute value and x and y equal to r, then T is a mapping from R to R is continuous at x naught belong to R such that if x minus if for every epsilon positive real number there is delta greater than 0 such that x minus x naught less than delta implies tx minus tx naught less than epsilon. So in case of usual metric, in case of x equal to r and d tilde usual metric, this definition in metric space of continuity of a function t from one metric space to another metric space at a point becomes this definition. You are familiar with this definition. So let me know if you are not. So that is the continuous mapping at a point. So can I rewrite it maybe this condition I can rewrite, or remember dx x naught be less than delta. So if a distance between x and x naught is less than delta, that means x belong to an open ball with center at x naught radius delta implies d tilde tx naught means and open ball around tx naught, tx belong to open ball around tx naught of radius epsilon. So this B is an open ball in the metric space xt, and this ball is in the metric space d tilde. So let me distinguish by writing d and d tilde. So in metric space, T is continuous at a point x naught. T is a mapping so we have this metric xt and we have this metric y d tilde. So T is a mapping from one metric space to another metric space. So T is continuous at a point x naught. X naught is a point here. And Tx image lies here in this set. So this T is continuous. So if for every epsilon, so you can draw an open ball of radius epsilon. So whatever is epsilon, you can pick epsilon of your own choice. So whatever for every positive number. So it can be small as you want, such that corresponding to this epsilon there exists an open ball around x naught of radius delta, such that if you pick any x from this and apply t on that, tx will fall here. So that is the continuity of
सर हम जब टोपोलॉजी पढ़ते हैं उसमें हम ये पढ़ते हैं प्री इमेज जो है ना, अगर कोई भी स्पेस है अगर वो ओपन है उसका प्री इमेज भी ओपन होना चाहिए, तो इनवर्स उसका चलता है।
yes.
तो आप कह रहे कि जो अगर ये ओपन है तो उसका इमेज ओपन होना चाहिए, लेकिन टोपोलॉजी में करते हैं उसका प्री इमेज ओपन होना चाहिए।
So at x naught, I will come to the topology definition as well now. So at x naught, it is continuous T if for every epsilon there is delta. That means if for every epsilon neighborhood or every open ball with radius epsilon with center at tx naught, there exists delta. Delta with there exists delta neighborhood, or maybe there exists open ball with radius delta with center at x naught. So whatever x you pick from open ball with radius delta, the image will be in the open ball with radius epsilon. So that is the definition of continuity. So T is continuous at x naught. So there is a result that I can ask you to read its proof from the book. So that is what you were saying. So let me discuss this theorem. Right? So a mapping T is continuous if and only if, sorry, I'm mapping T from one metric space xt to yd tilde is continuous if and only if every open subset of y if and only if the inverse image of every open set
ब्रेक नहीं होगी सर
every open subset of y is open in X. So this is actually equivalent to the definition of continuity. So T is continuous if you from X to Y, if you consider any open subset in Y and you compute the inverse image of that open set, that set is open in X. If it happens for every open subset of Y, then the mapping is continuous. So so what you were saying that is equivalent to the continuity. So you can consider it this definition in topology actually. So in topology there is no distance function in general. So but we have the definition of open sets in topology. So we have the concept of inverse image in topology. If a mapping T is from one topology to another, so you can use this criteria for the continuity of a mapping from one topological space to another. So every metric space is a topological space. So same you can use in the metric spaces as well in the form of this theorem. So this theorem, so you can read the proof in the book. So it shouldn't be much, you shouldn't have any problem in understanding, but if you will have, we can discuss. So now some people are asking for the break.
Yes, sir.
So you can have a break for
15 minutes.
सर 20 कर दे
okay 15 plus 20, the average of 15 and 20, right? It should be how much?
35 हो जाएंगे total.
35 divided by 2 average 17.5 minutes.
17.5
Yes. So, okay, so we have a break
8:20.
17.5 minutes.
सही हो गया.
So now time is 8:02.
804
जो
Two ही
मेरे
चलो
पास
सही हो
है,
गया.
804.
कोई नहीं सर,
okay,
2 मिनट
see
पीछे
you.
रख भी रहे तो हमारे 18 हो जाए, 19 हो जाएगा ना.
Okay, see you after 17.5 minutes.
Sir. Sir.
It is break.
Okay, thank you sir.
ये slides और ये recording वगैरह मिल जाएगी ना सर?
Yes, recording will be available. These slides will be available.
Thank you sir.
Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.
Thank you, sir.
आ जाएगा हम घबराएंगे
जी हेलो, वेलकम बैक।
जी सर।
Yes.
अस्सलाम वालेकुम सर।
Assalamu alaikum, sir.
जी अस्सलाम वालेकुम सर।
Alaikum.
So let me discuss some few definitions. So let M be a subset of metric space XT. X naught is an accumulation point. Point of M. If every neighborhood of contains at least one point of M. One point maybe Y of M such that Y is not equal to X naught. For example, if we have this metric space XT and M is a subset, and this point X naught is accumulation point. If you draw any neighborhood, or maybe if you draw any open wall around X naught, so it must intersect with M other than X naught. So there should be at least one point in the intersection of every open wall around X naught with M and M. So intersection of every open wall around X naught of any radius with M, this intersection should be non-empty. And this intersection should be other than this point X naught. Then we say that X naught is accumulation points. Accumulation point of the subset M. Or in other words, X naught is accumulation point if for every epsilon greater than 0. There is Y belong to M such that Y belong to V X naught epsilon intersection M. Or there is Y belong to X such that Y belong to the intersection and Y is not equal to X naught other than X naught.
सर ये y m में नहीं होगा?
Yes.
सर आपने x लिखा हुआ, y belongs to x.
Yeah, M is a subset of X. So if Y
तो
is
उस m से बाहर भी हो सकता है.
so Y belongs to M, because if Y belongs to the intersection, that means Y belongs to Bx not epsilon, and Y belongs to M. So Y belongs to M. So there should exist at least one point which belongs to the intersection. जो y m से बाहर होगा, the y that will not be in M may be the intersection of bx not epsilon with M is empty. So here we are saying that there is at least one point in the space which is in the intersection. So for example, so if you consider X equal to R, D as usual metric, and M is this set 0, 1, union 2, 3. So, okay, here we use the set of all accumulation points of M. Is denoted by M bar, M dash, this. So what is M dash? If M is 0, 1 closed interval union 2, 3, so what is the set of limit accumulation point?
0 and 1 closed interval.
Anam 0, Anam said M dash equal to 0 and 1.
0 and 1 closed interval.
Okay. So every point of this interval 0, 1 closed interval is an accumulation point. So 2 is not accumulation point.
Yes, sir.
2 does not belong to M dash, 3 does not belong to M dash. Why not?
So if we draw a neighborhood of, for example, 0.1 radius around 2, then it will not contain any point of M.
Yes. So if you draw a neighborhood or open ball around 2 of radius of half, so it will not intersect with M other than 2. So 2 is not the accumulation point. 3 is not the accumulation point with the same reason. So what if M is equal to 0, 1? So in that case, what is M dash?
Closed interval 0, 1.
Closed interval 0, 1, yes. 0 is a limit point. Every point is a accumulation point. The other name for accumulation point.
Limit point. Yes.
I'm saying limit point, accumulation
Limit
point.
point.
So every point of this closed and bounded interval 0, 1 is an accumulation point of this set. 0 is not in M, but 0 is in M dash, the accumulation point. So if you construct any open ball around 0, so it will contain many points of M. So it will intersect M other than
Yes.
0. The intersection is non-empty other than 0. Okay. So what about x equal to r? D is discrete metric. So D is discrete metric on R. And M is equal to this set. So let me ask a question. Is 2 belong to M dash?
नो सर।
नो सर, नहीं होगा
सर why not?
सर, क्योंकि अगर 2 के अराउंड एक अगर बाउंड्री बनाते हैं वो 3 और क्या नाम है 1 तक बन सकता है। 1 इंक्लूड ही नहीं है इसके अंदर, और ना है ऊपर 3 इंक्लूड है मिनिमम बाउंड्री।
ठीक है। So if you draw an open ball around 2 of radius half, it will not intersect with them other than 2. So what about 0? 0 belong to M dash or not?
Yes, sir.
Yes, sir.
Yes.
Yes, sir, because it is included.
सर 0 भी नहीं होगा।
सर 0 कैसे नहीं होगा? So why 0
सर
is
डिस्क्रीट में इसमें अगर हम वो रेडियस 1 ही लेते हैं तो ये भी 1 इंक्लूड नहीं कर रहा, और -1 आता है तो वो भी इंक्लूड नहीं करता है। -1 तो है नहीं, 1 बनता है वो इंक्लूड ही नहीं कर रहा सेट के अंदर, एम के अंदर।
So what is your answer? No?
Yes, sir. No.
No. Okay. So anyone with yes? So is there any accumulation point of M? So is there any point in M? Is there any point which is an accumulation point of M?
Yes, sir.
नो
1
सर।
Yes, sir. One.
सर
1 होगा।
1 तो सर 1 का नेबरहुड ड्रॉ करेंगे। जी सर 1 होगा।
Yes, sir. It's one.
जी
सर लेकिन 1 के अलावा कोई होना चाहिए ना। हम 1 के इर्द-गिर्द अगर नेबरहुड ड्रॉ करते हैं तो हमारा रेडियस जो है मतलब हमारी ओपन बॉल में जस्ट 1 पड़ा होगा। तो वी हैव टू फाइंड अ नंबर अदर देन 1।
Yes. So 1 belong to M dash?
नो।
No. So remember, open ball around any point for any x naught belong to R. Open ball of radius epsilon, where epsilon is less than or equal to 1. This open ball consists of only one point.
Yes, x naught.
So intersection with M minus this point x naught will always be empty.
Empty.
Yes. So no point is accumulation point. So there is no point actually. M dash is equal to empty. So these notions depend on the distance function d metric, right? So if you change the metric, maybe.
Sir, is it true that take a discrete metric, then there will be the no accumulation point?
So, well, who asked this question? Ghulam Murtaza?
No, sir, me, Dilawez.
Dilawez. So anyone would like to comment on what she said, Dilawez? So she said in general, I mean, her question is, so in
Yes, sir,
general,
in general.
if we have a discrete metric and we have a subset of the discrete metric, so what about the accumulation point of that subset, any subset, right?
सर एम्प्टी होगा हमेशा
Yes, sir.
डिस्क्रीट के केस में.
Yes,
Okay.
sir, I think the same.
Who thinks the same?
Me, Dilawez.
Okay, yes, because in the definition of accumulation point, we say that every open ball of any radius should intersect with the subset. So if you consider open ball with radius less than or equal to 1 around any point, so it will contain only one point, right? So it will not intersect with the subset other than that point. So there is no accumulation.
Accumulation.
So,
Thank you, sir.
Okay, so maybe you consider different metrics and check for the accumulation points. Consider, for example, L infinity, CAB, right? And LP spaces P greater or equal to 1 for practice, and consider the subset.
Bounded spaces.
Yes. So, okay. So there is another definition M bar, that is the closure of M. Closure of M is defined as M union M dash. If you consider the set itself with along with the set of accumulation points of the set. So if you consider the union of set and its accumulation point set, then that set is called closure of M. So it is the smallest closed set.
Is it smallest closed superset?
Yes, smallest closed set that contains M. So M closure is a closed set, right? What about set of limit points?
All limit points.
Is M dash a closed
All
set?
accumulation points.
Yes, sir.
How?
सर एम डैश अगर हम इसका मजीद लिमिट पॉइंट चेक करना चाहें एम डैश के ऊपर, तो एम डैश के दोबारा से एम डैश निकालेंगे तो वो सेम आ जाएगा और यूनियन पे फिर इसका एम डैश आएगा. मींस हम लिमिट पॉइंट्स का दोबारा लिमिट पॉइंट निकालते हैं वो तो खुद आ जाएगा ना.
Limit point sets. So you need. So M. So what is
Dash
M?
and then
M?
dash. It is equal to m dash.
maybe I have a question mark. So just try to write something. So how are you saying that m dash equal to m dash, right? You need to write some mathematics to show that m dash dash equal to m dash. So that is a question. So before we discuss closed set, so let me give you a criteria so that you can easily check given set is closed or not. Otherwise, you need to consider the complement of the set. If complement of the set is open, then the set is closed. Okay. So before we do that, there is another definition. So we will discuss in today's class a criteria for a set to be closed.
Sir, I think I read a theorem that a set is closed if and only if it contains the R limit points.
Yes. Yes, that is true if it contains all of its limit points.
Limit points.
Yes, you're right. So what about this set in discrete metric M? So is it closed?
No, it's not closed.
Why not?
It does not.
It does not contain limit points. Its limit points.
So can you tell me which limit point it does not contain?
So it does not have any limit point.
So you cannot give me a point which is the limit point and it does not contain. So it is closed.
Yes.
सर ये डिस्क्रीट मेट्रिक है, हर मेट्रिक टोपोलॉजी होती है और टोपोलॉजी में जो x होता है वो क्लोज भी होता है और ओपन भी होता है, तो ये तो क्लोज होगा.
Yes, discrete
So every metric is not topology, topological space.
It is topological space. So M is closed. So M is open as well.
Yes.
So
you mean to say M is both open and closed?
Yes. So every subset in a discrete metric is open and closed. So a set is closed if and only if it contains all of its limit points. So this condition is not being violated here. So let me, okay. So a subset M of X. So throughout this discussion, let Xt be a metric space. So I won't write again and again Xt is a metric space. So if it will be something else, I will let you know. So a subset M of X is dense in X if M closure equal to X. So example, the set of rational number is dense in R.
And irrational numbers?
Where R is equipped with Euclidean metric. Usual metric actually. We are using usual metric, this word. But Euclidean is also okay. Usual metric. So because Q closure is equal to R, Can you show that? So for example, if I write this question mark here, show that. Okay, we will come back to this question again, right?
सर इसके अंदर हमें क्यू के लिमिट पॉइंट्स निकालने होंगे, तो हम क्यू के जो खुद के एलिमेंट्स हैं वो तो ऑलरेडी मौजूद हैं, तो हम नेबरहुड्स ड्रॉ करेंगे। तो हम फॉर एग्जांपल इरेशनल नंबर पे नेबरहुड ड्रॉ करते हैं, तो हमारे पास एक थ्योरम है कि बिटवीन एवरी टू रैशनल नंबर देयर इज एन इरेशनल नंबर।
Yes.
We can use that. I mean this.
So we can prove this like that Q layer equals to Q unit Q derive, and the derived set of Q is a real number. So layer of
Yes.
Q is also real number.
Yes. So both are correct. So what they are saying actually, one Dilab is saying that Q closure is actually Q union Q dash, and Q dash is equal to R.
A real number R.
So the whole set of real number. So Q union R is equal to R. So the other person, who was the other student? Anam?
Yes, sir.
So Anam is saying that, for example, if you consider any R belong to R, right? And consider an open ball around any real number R of any epsilon. So that will consist of those real numbers whose distance from is less, R is strictly less than epsilon, and that is the set of X such that X minus R mod is less than epsilon. So what this set will be? This set will be R minus epsilon and R plus epsilon interval.
Yes.
So
if we take intersection with this ball Q.
So by Archimedean property.
Yes.
I'm sorry if I'm writing the spelling of Archimedean. I'm not sure whether I'm writing it right. So by Archimedean property. So what is Archimedean property? Archimedean property is between any two real numbers. For example, if you have two real numbers A and B, between any two real numbers, there is a rational number, there is an irrational number, both.
Yes.
So that means this R minus epsilon and R plus epsilon intersection with Q other than R.
Is non-empty.
Yes. Is non-empty. So this implies that R belongs to Q dash. So this implies that R is contained in Q dash, but Q dash is a subset of R as well. So what the Lewis said that Q dash is equal to R. So hence Q closure is equal to the set of real numbers. So you can revise these notions which are relevant from the real analysis as well, if there is any need.
Yes, sir.
So the other definition is X is separable. Okay, one interesting question. I will not write the question, but consider X equal to R and D as discrete metric. So then what is the closure of Q? So replace, so here we are considering the usual metric, but if you consider the discrete metric, so try to answer this question. So X is separable if it has a countable subset, countable dense subset. So for example, R is separable, R with the usual metric. Is separable as Q is countable and dense in R.
R.
Yes. So what does it mean by dense? M is dense in R, dense in X. That is M closure is equal to X. That is for any X belong to X. X belong to M closure, which is equal to M union
M dash.
M dash. So there are two possibilities. X belong to M or X belong to
M dash.
M dash. So consider if X belong to M dash. That means for any epsilon, Bx epsilon intersection with M is
Non-empty.
non-empty. So that means if this is your space X and M is this set, so whatever point you consider of X, and if you draw an open ball, so you will find points of M, just like the dense city. So what is a density? Every corner, wherever you are standing in the dense city. So if you draw a circle around you, so whatever is the radius of the circle, it doesn't matter. So it can be as small as you want. So you will find people in that circle. So that is a density. So every corner is filled with people. So roughly speaking. So then we call a city is dense. So a space, a set is dense in the space. So if everywhere, wherever you pick a point in the space and you draw open ball around that, it will contain the points in M. Then we say that M is dense in X. So here for every epsilon there is a for any epsilon intersection in empty is non-empty. What does it mean? That is, there exists a point X epsilon belong to Bx epsilon intersection M. But whatever is epsilon, you will find a point in the intersection. So for example, if epsilon is equal to n, 1 over n, then so 1 over n, where n belong to the set of natural number. So if you pick up, if n equal to 1, that means epsilon equal to 1. So you will get 1 point in the intersection corresponding to epsilon equal to 1. So for example, n equal to 1, you will get x1 belong to b x epsilon intersection m. For n equal to 2, you will get another point in the intersection. So up to so on. For n, you will get x. For m, you will get xm belong to bx epsilon. Epsilon is this one. So here I should write 1. Here I should write 1 by 2. Here I should write 1 over m. Intersection m. So continue. That means for any xn belong to bxn, sorry, bx 1 over n intersection empty. So this implies that xn belong to the ball. That means distance between xn and x is less than 1 over n. So if you consider limit on both sides, you will get dx and x is equal to 0. And these points are, where are these points? Belong to M. So if x is an accumulation point, if x is limit point, you can always get a sequence in M which converges to that point, converges to the accumulation point. So, well, somebody can say that we do not know what does it mean by limit of a sequence in metric space yet. So let me discuss, I'll come back to this point. So we'll discuss this theorem again. So in different setting. So we consider that the case when x belong to M dash. So you can consider x belong to M as well. Even then you can get a sequence which is constant sequence in M, which converges to that point. So okay, so there is a example in the book as well. That is L infinity is separable. Sorry, L infinity is not separable. L infinity is not separable, but LP, P greater equal to 1 are separable. L infinity is not. Okay, let me discuss briefly the proof L infinity is not separable. L infinity, so L infinity is the sequence space of all bounded sequences. So L infinity is endowed with the metric D, that is the supremum of xi I minus eta I belong to N, where x equal to xi I sequence and y is equal to eta I sequence. So L infinity is not separable. So you need to read the proof from the book. Let me give you the idea. So for example, if you have a number maybe 0.123 number between this interval 0, 1. So you can write 0.123, it has decimal representation, like you can write it as 1 over 10 plus 2 over 10 square plus 3 over 10 cube. So any number in this interval, you can write the decimal representation, this form. Similarly, there are many other number system, decimal number system, maybe binary number system, so tertiary number system. So for example, if you consider the sequences in L infinity that consist of either 0 or 1, zeros or ones. Like maybe this sequence 1 0 1 0 0 1 1 1. So this is a sequence of zeros or 1. So for a sequence, for such a sequence,
एक स्लाइड पीछे कीजिए प्लीज 1 मिनट के लिए। सर इससे पिछली प्लीज सर। थैंक यू सर।
so for such a sequence, let eta 1, eta 2 be a sequence of zeros and 1 or ones. So with such a sequence, maybe you can call it x tilde. With x, we can associate a real number. y tilde, that is equal to eta 1 over 2 plus eta 2 over 2 square plus eta 3 over 2 cube plus up to so on. You can define this number. So eta 1 is either 0 or 1, eta 2 is either 0 or 1, eta 3 is either 0 or 1. Then y tilde will be a number between 0, this interval. So this will be a number in the interval 0, 1. Also, for any number, for any real number r belong to 0, 1, there is a sequence of 0, 1, a sequence of zeros or ones such that r is equal to xi 1 over 2 plus xi 2 over 2 square plus up to so on xi n over 2 power n plus up to so on. So there is a sequence xi I of zeros and 1. So if you have a sequence of zeros or ones, and you can write this representation of such sequence, so that will be a number in the interval 0, 1. So if you pick any number from 0, 1 interval, so you can get a sequence of zeros or 1, so that number is equal to xi 1 over 2 plus xi 2 over 2 square plus up to so on. So any number in the 0, 1 can have this representation. So any sequence of zeros or 1 can be associated to such representation. And how many elements are there in 0, 1? Uncountably many.
Infinite.
Is uncountable.
Yes.
Is uncountable. So this set is uncountable. And we are so let capital Y is the set of all sequences of zeros and 1. For example, if you consider xy belong to capital Y, what will be the distance between xy?
Supremum of
Yes.
0
So
and minus 1.
So these are the sequences of zeros and 1 which are distinct. So distinct mean different. X is a different sequence of zeros and 1. Y is a different sequence of zeros and 1. So for example, there will be at least one place where the sequences will differ. So the supremum will be equal to 1.
1.
Yes. So now, if L infinity is separable, if L infinity is separable, so that means there is a countable dense subset. And if
Yes,
you
sir.
consider, so if you consider an open ball of radius, for example, for any x belong to capital Y, if you consider an open ball of radius 1/3, and any other y, so x and y are the sequences of 0 and 1. X is a sequence of 0 and 1. So consider the open ball with radius 1/3, intersection will be empty. So these balls will not intersect because the distance between x and y is 1. So if you consider open ball of radius 1 less than 1, 1/2, then these balls will not intersect. So if
Yes.
N is separable and there is a countable dense subset M, so that M has to intersect with each and every such ball. So these
Yes.
such balls are uncountably many such balls. So that means M cannot be countable. So if M has to be countable dense subset, it is not possible. So L infinity is separable because there are uncountably many such balls.
सर ये वाली जो balls हैं ये dense भी नहीं है ना, फिर countable भी नहीं है.
No,
ये मतलब
dense.
हम कोई subset, हमने dense subset find किया पहले एक 0 and 1.
No. We are saying, so in L infinity, there are uncountably many sequences of zeros and ones. So if you
Yes.
consider open ball around such sequences of radius less than 1/2,
Yes.
then these balls are uncountably many.
Okay.
So, and if there is L infinity is separable, that means there should be a countable dense subset. But
Yes.
due to the density, that subset must intersect with each and every such ball.
Yes.
So M will have that at least that many points as many there are balls. So that
Yes.
means M will be uncountable.
Yes.
So that is
ठीक है.
contradiction. So you will read this proof, you will understand hopefully. So if there will be any question, you can let me know. And also read the separability of LP. LP spaces are separable for each p greater or equal to 1. So read the L infinity is not separable and LP is separable for each p. So I will discuss the proof LP is separable, and in the next class we will discuss some convergence, Cauchiness and completeness in metric spaces. So maybe we will, I'm still struggling to have internet connection at home. I
Yes, sir.
shifted a couple of weeks before. So hopefully in a couple of days I will have, and then we can have a tutorial session.
Sir, which book you recommended for this subject?
Well, so far you can have this Kreyszig
Okay.
introductory functional analysis with application, and I will upload some books as well. So I will share a link to a folder in my Google Drive, so where I will put some other books as well.
सर यहाँ पर ना जो आपने नाम लिखा है ना सर, यहाँ पर लिख दें स्लाइड के ऊपर, आसानी हो जाएगी.
Okay, I will share the course outline. So I already have written the names of the books which we will discuss in this course, which we can study. So I will share the course outline via email.
Okay, sir.
Thank you, sir.
So, okay, is there any question, comment?
Yes, sir.
Yes, sir.
Sir, you
Yes.
have discussed the question that we have to discuss a density. We have to discuss the dense set of Q if X is discrete metric space. You raise a question that we have to discuss the density of Q if X is discrete metric space.
Yes. Yes.
Uh,
So what is your question?
I think for discrete, if X is discrete metric space, then Q is dense, I think, in R.
Okay, so please write the solution and maybe we will discuss in the next class. So that is question for today. So you can view your solution if you already have solved it. And maybe you can send the picture via email. So I will check if it is okay. Otherwise, I will discuss the solution in the next class.
यस सर और सर आपने लास्ट टाइम पे एक असाइनमेंट दी थी कि मिनिमम एंड इन्फिमम आर दिस मैट्रिक्स और नॉट मिनिमम और इन्फिमम और इन्फिमम तो सर वो नहीं बनाते क्योंकि हमारे पास काफी सारी काउंटर एग्जांपल्स आ जाती हैं.
Okay, so
CAB page.
Your answer is correct. So, but can you write on 1 page or 2 page? Maybe we can share with other people as well.
Yes, sir. I will share it.
Is there any question, comment?
Yes, sir. Sir, आप कल कितने बजे ऑफिस में होंगे?
That is what I don't know.
चलो सही मैं चक्कर लगा लेता हूँ देखता हूँ आप होंगे तो मैं आ जाता हूँ
अपने काइंडली ऑफिस आवर्स भी शेयर कर दें.
So I have a class tomorrow at 12:30. But if I leave, then
सही यूनिवर्सिटी में अलावा स्टूडेंट्स का आना
university may allow many students to come. Students cannot come because what if there is any
सर ये आवाज ठीक नहीं आ रही पीछे से किसी का ना माइक जो है ऑन है काइंडली बंद करो.
Okay, so can you please mute your mic if there is a noise on your side? So students I think who are involved in research, they can come, and for that the concerned teacher has to send an email to the security office, so then they can visit. So I think we should have virtual office hours via Zoom.
सर हमें जो मेल आई थी उसमें लिखा हुआ है कि आप अपने सुपरवाइजर से जो है वो पीएचडी स्टूडेंट एमफिल वाले जो हैं वो ऑनलाइन जो है वो कंसल्ट कर सकते हैं.
Yes, PhD students.
तो ऑन कैंपस नहीं अलाउड.
On campus nahi allowed, but some students are allowed, but we need to send an email in advance. So it is not possible that you come at the gate and they will allow you to enter. So they will ask, is there any email from your instructor or supervisor? So if you won't have any email, they probably won't allow you. So if you are planning, you can send me or you can send email to any teacher, so we can forward so that you can come.
Okay, sir. Thank you so much.
Okay.
Thank you, sir.
Yes.
Thank you, sir.
So if there is no question, comment, you can ask me in the email. So there is an email. You can have a WhatsApp group as well if you would like. So
sir, we have a WhatsApp group.
Sir, kindly add me in that group.
You can add me if you do not have too many notifications in the group.
Yes, sir.
Sir, we have already a WhatsApp group, but because your number is not
If you do not have my number, whoever is the admin can send me an email. I will send my number, but do not add me in the group. So I can be in touch with the admin. So if there is any information, I can pass to the admin, and an admin can share in the group.
Okay, sir. I will send a mail.
Yes, and okay.
Thank
So
you,
okay,
sir.
we will discuss via WhatsApp, and you can send me an email or whatever you feel better.
सर एक और स्टूडेंट से हमारे साथ पीएचडी की, उनका क्या नेम है? अभी आई थिंक क्लास में नहीं है।
अनम रियाज है तो
अनम रियाज and
अनम
सादिया.
रियाज। सर मैं सादिया फारूक, मैं अनम जो है वो फिक्स पॉइंट थ्योरी में काम कर रही हैं।
नहीं, मेरा फर्स्ट सेमेस्टर है, मैंने अभी काम नहीं स्टार्ट किया।
नहीं, आपका वैसे एमफिल फिक्स पॉइंट थ्योरी में था?
नहीं, मेरा ग्रुप थ्योरी में था।
ओके, ठीक है।
तो
चलें, अगर किसी स्टूडेंट को प्रॉब्लम हो तो आपको डायरेक्ट ईमेल करें या एडमिन को मैसेज करें?
एडमिन को मैसेज कर दें, मुझे ईमेल कर दें, इट इज फाइन। So well, there are two students from Afghanistan we have in our class. So they do not understand Urdu. So if you have any question or sometime, I mean, for them you can also speak in English as well. If there is any question, so they can.
Yes, thank you, sir. Thank you, sir.
So we can involve them in the discussion.
सर वो कह रहे हैं कि उनको उर्दू की समझ आती है।
Okay, that's good then.
So their name?
They understand Urdu. Noor Rahman.
Yes, sir. Yes, sir.
So any problem? So any question, comments?
No, I don't have.
Okay. So I will share the recording in some time. So I will share the lecture slides as well. So I will share the link to a folder in my Google Drive where you can find these things. So any material related to the course you can find in the folder in the Google Drive. So I will try to do. Okay. So okay, I will end this meeting. I wish you all the best. So Allah Hafiz.
Thank you so much, dear teacher.
Allah Hafiz.